Hello everyone, welcome to this channel. If you're new here, my name is Hasan. Let's begin our 18th part of the video series. In this video, I'll be discussing about the concept of magnification. A little bit of magnification has already been done in my earlier video. In this video, I'll be discussing the formula of magnification based on image distance and object distance. That is the formula for magnification in terms of V and U. We'll be looking into that and then we'll solve some problem in order to solidify the concept. Okay, next we'll jump into the concept of combination of lengths. That is what will be the equivalent focal length whenever lenses are joined together. Okay, so we'll be looking into that. We'll find the equivalent focal length, derive the expression, and then directly jump into the numerical based on that formula. Okay, this is a bit important concept because last year in NEET question was asked based on this concept. Okay, so I'll also discuss the question that was asked in the earlier year, that is in the year 2019. I'll discuss that and I'll also give you the trick in order to solve that question within 1 minute because it's a bit lengthy question, but if you know the trick you can solve it within 1 minute. So let's jump into our concept building process and enjoy the process, and let's roll the intro. Okay, let's start our study on the concept of magnification in lens. We already know some concept related to magnification. A little bit is still left, so we'll be looking into that and then wrap up the concept of magnification in lens. So let's see the definition of magnification. You know that magnification is basically the ratio of height of image to height of object. Actually, what we are doing, we are just comparing the size of image to that of the size of object. Therefore, magnification is hi by ho, and this thing we have already done. The important thing that you need to remember about this formula is that the value of hi and the value of ho should be used with proper sign, as I've written it down here. Okay, this should be used with proper sign. Don't be in a hurry and just put the magnitude of hi and ho. You'll get wrong answer because you know that magnification, positive and negative magnification, denote absolutely different thing. So if you just miss out the sign convention, then you'll get a total different result, even though your magnitude may be correct. Okay, so sign is very important when it comes to the formula for magnification. And I've already explained the sign convention related to height. So in short, I can say that height of a principal axis is taken as positive and height below principal axis, as you can see it here, is taken as negative. So simply, if an object is like this, then we'll take it as positive if this is the lens, and if the image is in this side, then we can take this as negative because we are going below the principal axis, and this is going above the principal axis, so we'll be taking it as positive. I hope the concept is clear. So this is the basic fundamental concept of magnification. Now the important thing that we need to know about magnification is the formula for magnification in terms of U and V, that is object distance and image distance, which is the most important formula for magnification, and most of the numerical based on magnification can be solved using that formula. So we'll be deriving that formula of magnification. So let's look into that. So let's see the derivation of magnification in terms of U and V. As you can see it in the figure ray diagram, that we have taken the object to be AB here. Okay, and we know for production of image or formation of image, we at least require two rays for intersection. So we have taken two rays, one with blue color, another with green color. So let it be the first ray and this be the second ray. Okay, so this ray is moving parallel to principal axis, the number one ray. Okay, so after refraction, we know it will pass through focus. As you can see it here, this is the primary focus, that is f2. Now the second ray, as you can see in green color, is passing through the optical center, therefore it will go undeviated and the ray will meet at this point, and as you can see, this is the object formed at the intersection. Okay, this is clear. This is just the ray diagram. Now this is U, that is the object distance from the lens, and this is V, the image distance from the lens. This is clear. Now let's understand one thing. If you take into consideration two triangles, now let me shade this triangle. So this is one of the triangle ABO, and this is the second triangle A dash B dash and O, as you can see it in the figure. Okay, now we'll be comparing this triangle. If you look into the screen, then we have written that triangle AOB is similar to triangle A dash B dash O. We know two triangles are similar when all the angles of the triangle for both the triangle are similar. So we can see, let's analyze that. See, this angle will be equal to this angle because vertically opposite. This angle B is 90 degree and B dash will also be 90 degree, as you can see it here, both are 90 degree. Okay, so since two of the angles of the triangle is equal, therefore the third angle, that is angle A here and angle A dash here, has to be equal. Okay, therefore we can say that since triangle AOB and A dash B dash O dash are similar, we can use the property of similar triangle, that is A dash B dash divided by AB is equal to OB dash by OB. You can just pause the video and check. I've used the property of similar triangle. Okay. Now, therefore, we can write that A dash B dash can be written as minus HI. Okay. Look into this figure. If you look here, then you'll see that A dash B dash is actually moving below the principal axis. Therefore, we'll take negative sign, whereas AB is moving above the principal axis, as you can see it here. Therefore, we will take it as positive HO. Now, OB dash, if you look there, then that is actually the image distance from the optical center. So we have written it V, and OB, if you look into the figure again, then this is basically the object distance from the optical center. I hope this is clear. Now if you just solve this minus, and this minus will get cancelled out, and we got that HI by HO is equal to V by U. Now we know that magnification is basically HI by HO. Therefore we can say that magnification here is equal to V by U. From here we can say it that this is the formula for magnification in terms of V and U. Okay, so this is the formula that you need to remember also. So this is all about the derivation of magnification in terms of V and U. You need to remember this. Now let's move on to our next concept. Now let's look into some of the concept that you need to understand from magnification. Now these things you already know, so I'll move very fast. Okay, so the first thing is that whenever the magnification is positive, then the two things that you need to remember is that the image produced is upright or erect. Whenever M is positive, the first thing that should come up that the image produced is upright or erect. And if the image produced is upright, then the image has to be virtual. And whenever M is negative, then the image produced is inverted. Always negative M signifies that the image produced is inverted. And if the image is inverted, the next conclusion is that the image should be real. Okay, so these are the two things that you need to remember. Again, when M is positive, first thing that should come up is that the image produced is upright. And since the image produced is upright, the image has to be virtual. Second case, when M is negative, the first thing that should come up to your mind is that image produced is inverted. And if the image is inverted, then the image has to be real. Now the last 2 points is very important. These points should be engraved in your brain. Okay, you should never forget this. This is very important. Now convex lens show both positive as well as negative magnification. Why? Because we know that convex lens produce both virtual as well as real image. It can produce both. We know that for convex lens, whenever the object is kept between infinity to focus, then the image produced is always real, as you have seen. And whenever the object is between focus and optical center for convex lens, then we always get a virtual image and the image is enlarged. Okay, and for the concave lens, you need to remember that it always gives positive magnification. Okay, positive magnification means the image produced is always virtual. Okay, we know that for concave lens, wherever be the object, doesn't matter, it always produce virtual image and the image is always diminished. Okay, these are the things I've already explained. So these are the concepts that you need to understand when it comes to the concept of magnification for lens. Now let's move on to our next concept, that is we'll be comparing the concept of magnification for lens and mirror. So let's move on. Now if you look into this comparison chart that I have created for you, that is for mirror and lens, we see that magnification for mirror is given to be HI by HO, and in terms of V and U, it is given to be M is equal to minus V by U, isn't it? Whereas for lens, we can see that even though the definition is HI by HO, we are getting the formula to be V by U. So there is no negative when it comes to lens. But for mirror formula, we got 1 by F is equal to 1 by V plus 1 by U. But for lens formula, we got 1 by F is equal to 1 by V minus 1 by U. So don't ever confuse this. The easiest way I think you can use this technique to remember this, that if you look into this formula, then it has positive, so the magnification will have negative. Okay, if you look into this formula, since this lens formula has negative, then the magnification will have positive. Just the opposite. You can remember it in this way. So if you just remember this mirror formula, you know magnification term will have negative because it has positive. Okay, and if you just remember this formula, you know it will be negative for lens, and if this is negative, then this has to be positive. So you can remember it in this way without forgetting. So if you just remember one formula, one of the signs of the formula, then other signs of the three formula can easily be derived. Okay, just by this technique. So this is the comparison that I need to explain. Okay, now let's look into some of the problems related to magnification, and things will be very, very clear. Okay, now let's look into this problem, and if you just understand this problem, the concept of magnification will be absolutely clear. So let's look into this. A convex lens has focal length is equal to 12 centimeter. Find the distance of object from the lens if the image formed is number 1 virtual and 3 times the size of object, and number 2 the image formed is real and 3 times the size of object. Okay, first we'll be looking into number 1. Okay, so let's see the solution. The first thing that you need to remember is whenever the image formed is virtual, the most important thing is magnification is always taken to be positive. The most important part for this question. Okay, therefore we know that magnification is v by u, isn't it, for lens, and it's given that the magnification is 3 times. Therefore we can say that m is plus 3 is equal to v by u, or we can say that 3u is equal to v. Okay, now in the question it is asked where is the object kept. Okay, so you need to find out the object distance, and the focal length is given, so the only formula that you can think of is the length formula. 1 by f is equal to 1 by v minus 1 by u. Now you need to find u, and f is given, so one thing you can do to solve this formula is find out v in terms of u, then you can find out u. So you can find v in terms of u from this formula. Okay, and you can put it here. Once you can put it here, then you will get 1 by f is equal to 1 by 3u minus 1 by u. Now f is given to be 12 centimeter, but this is a convex lens. We know the focal length for convex lens is always positive, so it is 1 by plus 12 is equal to 1 by 3u minus 1 by u. Now if you solve this, you're going to get u is equal to minus 8 centimeter. Now if I draw this thing roughly, then we are going to get that the object is kept somewhat here, and the distance is, if this is the object, then the distance is 8 centimeter in front of the lens, and this will be the focus, that is 12 centimeter from the lens. Okay, I hope this is clear, and this is the optical center. Now one thing you need to understand here is that the answer is actually satisfying the concept. We know that whenever the object is kept in between focus and optical center, then the image is always virtual, isn't it? We have learned this thing in the video where I've discussed image formation due to lens. Okay, so you can see that the concept is actually satisfying here, that whenever the object is kept between focus and optical center, then we are getting virtual image, and the virtual image that we always received in convex lens is always greater. So whenever virtual image is formed, it is always bigger than the object. Okay, so all the concepts, as you can see, is matching. Therefore our concept is correct and our answer is correct. So the first question is done. Now if you look into the second question, then again concept is very easy. It says that the image formed is real and 3 times the size of the object. Now if the image is real, then magnification is taken to be negative. Okay, therefore we can say, since the magnification is 3, so and the image formed is real, therefore we can say minus 3 is equal to v by u this time, isn't it? So you can say that v is equal to minus 3u. Now you need to find out the object distance. So the only thing you can do is use the lens formula, that is 1 by f is equal to 1 by v minus 1 by u. Simple, it's very simple. We know the focal length for convex lens is positive, so we can take plus 12, and 1 by v, since we need to find out u, we'll be using v in terms of u from this equation. Okay, so v is minus 3u minus 1 by u. Okay, now if we solve this, we are going to get u is equal to minus 16 centimeter. Again, if we draw the scenario, it will match with our concepts that we have already learned. So if this is our focus and the distance is 12 centimeter, okay, this is our focus. Now the object is at 16 centimeter, so our object is somewhat here. This is our object, that is 16 centimeter in front of the lens. Now we have learned that whenever the object is kept between infinity and focus, okay, then we always get real image, isn't it? And see, in our question we got real image because magnification is negative. Okay, as you can see, so our concept is matching with our answer, therefore our answer is correct. Okay, so this is all about the concept of magnification you need to use whenever questions are asked based on magnification. You need to understand one thing: whenever the image formed is real, then magnification is negative, and whenever image formed is virtual, magnification is positive. You need to remember this. Okay, and the second thing you need to remember is that whenever you need to find out the object distance, you need to find out v in terms of u, and whenever you need to find out image distance, then you need to find out u in terms of v and then put it in the length formula. I hope this is the pattern that you need to follow in order to solve this kind of question. I hope the concept is clear. Now let's move on to our next question, and it will be the final question for magnification. And I hope that whenever questions are asked from this part, you can easily smash those questions. Now let's look on to our next problem. Okay, now let's look into this question. It says a lens of focal length 10 centimeter is given, forms an upright image which is half the size of the object. Find nature of lens and calculate object distance. So you can see in this question, it's not said whether the lens is a concave lens or a convex lens. Okay, therefore you cannot say whether the focal length will be positive or negative because we don't know which lens is used. So we need to understand how to decipher which lens it is, whether it's a concave lens or a convex lens. One of the clue that is given in the question is that the image that is formed is upright image and the size is half. From this two clue we can find out whether the lens is a concave or a convex lens. So let's see. First of all, understand since the image is upright, therefore magnification has to be positive. Why? Because if the image is upright, okay, let me write it down, then we know the image is actually virtual image always. And if the image is virtual, then magnification is always positive. Therefore, you can say that m is equal to v by u, or the magnification is given to be half because it says that the image is half the size of object. So you can say plus half, since magnification is positive because of the virtual image, is equal to v by u, or we can say that v is equal to half u. This is done. Now in the question it is asked, find the nature of lens and calculate the object distance. So you need to find out object distance and focal length is given. Okay, so the basic formula that we'll be using is lens's formula. Okay, and the formula says that 1 by f is equal to 1 by v minus 1 by u. Now since we need to find u, we will put the value of v in terms of u from here and we will get the value of u. But the problem is, what will be the value of focal length? Basically, what will be the sign of the focal length, because we don't know whether it's a convex or a concave lens. Now, how to understand this? The image that is formed is virtual and it is diminished because the size is half the size of the object. Now, if you know the property that only one lens can give virtual and diminished image, okay, and that lens is actually concave lens. If you look into lens, then there are two lenses, concave and convex. Now convex produces virtual image, isn't it? But it is always magnified, whereas concave, from the property we know, it always produces virtual, whereas convex can produce virtual as well as real. Okay, but concave always produces virtual and the virtual image is always diminished. This is very important. While I was explaining the property, I said and stressed upon that, and I also marked it a star because this is a very important concept. So we can say, since the image is virtual and it is diminished, we can say that the lens is a concave lens, and we know the focal length of a concave lens is always negative, so we can say it is minus 10, and v can be written as half u, so we can say that it is 2 by u minus 1 by u. Now if we start solving this, then we will get minus 1 by 10 is equal to 1 by u, or basically you can say that u is equal to minus 10 centimeter. That is, if this is our concave lens, okay, then our object will be in this side, which is 10 centimeter in front of the lens. Okay, I hope the concept is clear. Now let's move on to our next concept. Okay, now let's start our study on this new concept, that is combination of thin lenses. This is a bit important concept when it comes to NEET, and last year question was asked best on this concept, so please concentrate here and things will be very easy. Now let's look into this. Since there are two lenses having focal length f1 and f2, as you can see, we will take one at a time to find out the equivalent focal length. The concept here is that we need to find out the equivalent focal length for the combination of the lenses. Okay, this is our task. So it's very simple. Let's take into consideration refraction from the first lens, then what we'll get. Now this is the object, as you can see. Okay, we require two rays for formation of image. So this is our first ray and this is our second ray moving along the principal axis. The ray that is moving along the principal axis will not deviate, and the ray, this is the first ray, this after refraction will converge to a point because convex lens is a converging lens. Okay, both the rays will intersect at this point and an image will be formed known as I dash here. Okay, because this is not the final image. This is just the first part of the combination. Now we want to find out the location of this image formed. So very easy. So we'll be using Lenz's formula, that is 1 by f1 is equal to 1 by v dash minus 1 by u. Now u is the object distance, so this is the object distance u, and v dash is the image distance which is produced due to refraction by the first lens. Simple as that. So this is our first equation, very important. Now we will take into consideration our second case. So we can write it here that this is the first case, that is refraction from the first lens. Now for the second case, we can see the refraction will take place from the second lens. So what will happen? Now this thing we have already learned, this concept that I'm going to tell, that this is the image that is formed due to refraction from the first lens. Okay, so now for the second lens, this image will act as virtual object for the second lens, and this concept have been taught in my earlier videos when I was explaining various kind of combination. This thing only occur whenever combination comes into play. Okay, that is the result of the first stage acts as a virtual object for the second stage. Okay, I hope this is clear. Now let's look into that. Therefore, if we apply Lenz's formula for the second case, we can get that 1 by f2 is equal to, now if I take another color, because this ray, as you can see it here, the orange color, will go here and will refract again and will converge more because the second lens is also a converging lens, that is convex lens, and the image, final image, will be produced here. Okay, because this is our second ray. Okay, so we got the final image to be here. Therefore we can say that this distance is actually the final image distance v. Okay, so we'll apply the Lenz's formula for that. So we know that 1 by f, here f is f2, is equal to 1 by v. Image distance here is v, and the object distance will be v dash, because this distance is actually the object distance, because this image is actually acting as a virtual object for the second lens. I hope this much is clear. So this is our second equation. Now adding equation 1 and 2, what we are going to get is that 1 by f1 plus 1 by f2 is, now if you look carefully, then this minus 1 by v dash and plus 1 by v dash will get cancelled out. So we are left with 1 by v minus 1 by u. So this is our third equation. I hope this is clear. Simple, it's very easy. Now what we are going to do is understand this part. This is the final part. If we replace this combination of thin lenses as like this, so this is the combined lens, and we can say that the focal length is Fe, that is the combined focal length of this lens and this lens. Okay, similarly, as we have learned earlier in physics that this is resistance and this is resistance, we can combine these two resistance and write this as a single resistance and name this as equivalent resistance, isn't it? The same concept we are applying here. Here we have taken two lenses having focal length f1 and f2, and then we are combining those two lenses and writing this as single lens having focal length fe. Now if we keep the same object here at a distance u, then where will the image form? The image will form at a distance v, isn't it? This will be the image. I hope this much is clear. So if we apply Lenz's formula for this combination, then we can say that 1 by fe will be equal to 1 by v minus 1 by u. So this is our fourth equation. Now if we compare equation 3 and 4, so we can write it here, comparing equation 3 and 4, we can see that the right hand side is similar. Therefore, the left hand side should also be similar. Therefore, if we compare equation 3 and 4, then we can say that 1 by fe, that is equivalent focal length for this lens, is basically 1 by f1 plus 1 by f2. Okay? Because this scenario, as you can see it here, this scenario is same as this scenario. Okay? We are writing these two lenses into a single one. Okay? And the result will be same. Okay, so we can say that the equivalent focal length 1 by fe is equal to 1 by f1 plus 1 by f2. Now the important thing that you need to understand for this formula, now let's dissect this formula in order to make things more clear, that the value of f1 and f2 should be used with proper sign. Okay, I've taken into account here in this example both lenses as convex lens, okay? But the formula will remain same if we use any lenses, whether it's convex or concave. The equivalent focal length will be equal to 1 by f1 plus 1 by f2. Now, if the number of lenses increases, like if more than 2 lenses come into play, then what will happen? Then we can simply say 1 by f equivalent is equal to 1 by f1 plus 1 by f2 plus 1 by f3 dot 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 dot, and it will go on depending on the number of lenses. Okay, I hope this much is clear. And the value of f1, f2, f3, f4, all these values should be used with proper sign. I hope this is clear, because the focal length is positive for convex lens and focal length is negative for concave lens. You need to keep this in mind. So this is the formula that you need to remember. So let me write it down in a fresh way. That is 1 by fe is equal to 1 by f1 plus 1 by f2 plus 1 by f3 dot dot dot, where 1 by fe or fe is the equivalent focal length of the lens. Okay, I hope this is clear. So this is the formula that is very important. Now I'll be looking into some of the numerical problems in order to make this concept absolutely solid. Okay, so let's jump into that. Okay, so let's look into this question, and the concept of combination of lens will be very clear. Now, it's given that a concave lens having focal length 10 cm and a convex lens having focal length 5 cm is given, and they're combined together. Okay, so what will be the equivalent focal length? This is the first question. And the second question is find the location of image for an object 15 cm from the combination. Okay, that is the object is kept 15 cm from the combined lens. So let's look into the first question and see how to solve that. It's easy. We know that whenever lenses are combined, the equivalent focal length is given by 1 by f is equal to 1 by f1 plus 1 by f2, and it will go on depending on the number of lenses. But here, as you can see, that there are two lenses, one is concave and other is convex, so we'll be writing 1 by f1 plus 1 by f2. Okay, now for this formula I said that the value of f1 and f2 should be written with proper sign. So as you can see, there are two lenses, one is concave, one is convex, therefore focal length will have different signs, so we'll be using that. So let's see. Therefore we can write that 1 by fe is equal to 1 by f1. Now f1 for concave lens, the focal length is given to be 10 cm, and we know that the sign will be negative for concave. Therefore we will write that f1 as minus 10 cm, plus we know the focal length for convex lens is always taken as positive, so f2 will be plus 5 cm. Okay, now if we solve this, then we are going to get LCM as 10, and here will be minus 1, and here it will be plus 2, and we are ultimately going to get 1 by 10 is equal to 1 by fe, or therefore we can say that fe is equal to 10 cm plus 10 cm. Therefore, if the question is asked, how will the lens behave, the combined lens behave, then your answer should be the combined lens should behave as a convex lens. Why? Because the combined focal length is actually coming out to be plus. Therefore, the combined lens will act as a convex lens. That is, it will ultimately converge the rays. Okay, I hope this is clear. So this is the equivalent focal length. And number 2 question is, what will be the position of image for an object? This is our suppose combined focal length fe, and our object is kept 15 cm in front of the lens. Okay, so we can write here as 15. So where will be the image formed? That is, you need to find out the value of v. We know that in order to find the location of image, we always use Lenz's formula whenever there is no refractive index mentioned. Okay, so we can write 1 by fe is equal to 1 by v minus 1 by u. Okay, now the combined focal length is given to be plus 10 cm. So we can write down 1 by 10 is equal to, we need to find out v minus of u. Now u will be taken as minus 15 cm according to sign convention. I won't explain that. I hope you know that. Okay, so if you solve this, then it will be 1 by 10 minus 1 by 15 will be equal to 1 by v. Or we can write it down here that 1 by v will be, now if you take the LCM, then it will be 30, then it will be 3 minus 2, and it will be 1 by 30. Therefore we can say that v will be plus 30 cm. Therefore we can say that the image will be formed somewhere here on the opposite side of the lens at a distance 30 centimeter. I hope this is clear. So this is how you need to solve this kind of question whenever lens combination is asked. I hope how to use the formula for combination of lens is now clear, how to use that value with proper sign. If this is clear, now let's move on to a bit complicated question, and after that your concept will be absolutely clear. So let's move into that. Now let's look into this problem. This question was asked last year, that is NEET 2019, and it's a bit conceptual problem, so let's look into that. Two similar thin equiconvex lens of focal length f each are kept coaxially in contact with each other such that the focal length of the combination is f1. When the space between the two lenses is filled with glycerin which has the same refractive index mu is equal to 1.5 as that of the glass, then the equivalent focal length is f2. Then we need to find out the ratio of f1 is to f2. Basically what it's trying to say is that these are two equiconvex, or we can say biconvex lens. Equiconvex means r1 is equal to r2. Okay, so this is having focal length f and this is also having focal length f, and the refractive index of these two lenses are given to be 1.5. okay, and it says the combined focal length fe for this combined lenses is given to be f1. okay, the first important concept that you need to understand is that focal length for lens depends upon two things. Okay, so let me write that. Depends upon number one, that is refractive index of the lens, and number two, radius of curvature. Okay, and we have seen this in the formula, lens maker's formula, that is 1 by f is equal to refractive index of lens divided by refractive index of the medium in which the lens is kept minus 1 multiplied by 1 by r1 minus 1 by r2. So if we change the refractive index or r, what will happen? The focal length will change. So these two parameters are very, very important. So you need to remember this concept. And in order to solve this kind of question, the first thing you need to understand is you need to find out focal length, okay, in terms of radius of curvature. Okay, so the first step, find focal length in terms of r. Now since the lenses are equiconvex lens, therefore r1 will be equal to r2, can be written as r. Okay, this is actually equiconvex, that is both the radius of curvature of both the surfaces will be same. So let's find out the focal length in terms of r. 1 by f is equal to refractive index of the lens is given to be 1.5 and is kept in air, so refractive index of air is 1 minus 1 multiplied by 1 by r minus 1 by r, because r1 and r2 is same. Now let's understand. If we draw the convex lens, then this surface is the first surface r1 and this is the second surface r2. Now the incident ray direction is this side, so we calculate r1 in this side for the first surface, so r1 will be positive, and r2 we calculate in this direction, so r2 will be negative. So we can say that this r2 will be negative, so negative negative becomes positive. So ultimately we can write that 1.5 minus 1 is actually half, that is 0.5 multiplied by 1 by r plus 1 by r is 2 by r. Okay, and 2 got cancelled, so we can write that 1 by r. So we found out the focal length for each lens, that is f, is equal to r. Okay, since both the lenses are same, therefore both the focal length will be same. Now let's understand the scenario. Once we have found out the focal length in terms of r, now the second step of this question is that if these are the convex lens kept in contact, okay, and glycerin is put in between these two lenses, suppose this is the glycerin, having the refractive index same as that of the glass, that is refractive index is 1.5. so our next step, second step, is finding focal length of this concave lens in terms of r again. Okay, so let's see. 1 by f for this lens, okay, 1 by f is equal to refractive index of this layer, so refractive index is given to be 1.5, so 1.5, it is kept in air, so 1 minus 1 multiplied. Now let's look into this. If this is the r1 surface, okay, and this is second surface, So it is sharing the same surface as that of convex lens, and we know the radius of curvature for the convex lens was same on both the side r. So the radius of curvature for the concave lens will also be r because it is sharing the same surfaces with the convex. Therefore, we can say both the r1 and r2 will be r. I hope this is clear. If you just pause this video and then think, and it will be clear for you. Okay, so this can be written as 1 by r minus 1 by r2, which is also r. Now let's put the sign convention for r. Now if this is our convex lens and this is R1 and this is R2, if you look into the figure, the incident ray will be in this direction and R1 will be calculated in this way from the pole. So R1 is negative and R2 will be calculated in this direction. So R2 is positive. So we'll put R1 as negative, R2 as positive, and we will calculate. Okay, so if we calculate, then we will get this as half multiplied by minus 1 by r minus 1 by r is minus 2 by r, and 2 got cancelled. So basically what we are getting is 1 by f is equal to minus 1 by r. Okay, therefore we can say focal length is minus r. Obviously we'll get negative because it's a concave lens. Now we got the focal length of the convex lens as r and the focal length of the concave lens as minus r. So we got three lenses. So the first lens, if you look into this combination again, let's draw the combination. So this is our first lens. This is our second lens, that is concave, and this is our third lens. Okay, so we can say the equivalent focal length for these combined lenses are 1 by f1 plus 1 by f2 plus 1 by f3. Now f1 is a convex lens having focal length r because we have found out f1 to be r, so it is 1 by r, plus f2 we found out it's a concave lens and the focal length is minus r, so we will write it out as 1 by minus r, plus f3 is again the same convex lens, so it will be 1 by plus r. So minus 1 by r plus 1 by r got cancelled, so the combined focal length is basically r. Okay, now this is f2, isn't it? Because it says, if you look into the question, it says you need to find out the ratio of f1 by f2. F1 is the combination when no glycerin was present in between the convex lens, and this is f2 when glycerin is used between the convex lens. So we got f2 as r. Now in order to find f1, again it's very easy. So you can say that 1 by f1 is equal to, if we combine both the convex lens, we know the focal length for convex lens is r. So 1 by r plus 1 by r, we can find out that f1 is equal to r by 2. Okay, therefore the ratio of f1 is to f2 is r by 2 divided by r. Okay, so basically it is half. Okay, so this is the basic steps in which you need to solve this question. That is, you need to find out focal length in terms of r, okay, and then compare. But since this was asked in NEET, and we know in NEET most of the question can be solved within 1 minute. So how to solve this question in 1 minute? Let's understand that. Okay, so let's see. If you analyze, this is our convex lens, okay, having focal length f, and this will have focal length f. The most important thing is the clue that's given here is that the refractive index of the glass is 1.5 and the refractive index of this glycerin is same as that of the glass lens, that is mu is equal to 1.5. Okay, now understand one thing, focal length depends upon two things. Again, see how we are applying the concept. It depends upon refractive index and it depends upon radius of curvature. Now if you look into the property of convex and the concave lens, because this is the convex lens and this is the concave lens, okay, both the convex and the concave lens has the same refractive index and it is having the same radius of curvature. Therefore we can say all the focal lengths are same for both the concave and the convex lens. Therefore the focal length for convex will be plus f and focal length of concave lens will be minus f. The magnitude will be same. One of the only difference is that the convex lens will have positive sign because positive sign indicates that the rays are converging and the negative sign indicates that the rays are diverging. Okay, but the magnitude will be same. Why? Because refractive index and radius of curvature for both the lenses are same. So now it's very easy. f1 by f2, if we combine these three, then we are going to get 1 by plus f plus of 1 by minus f plus of 1 by plus f. Okay, so this got cancelled, so we are ultimately getting f2 as f. Okay, now if you find f1, that is combining just the convex lenses, then 1 by f1 is equal to 1 by f plus 1 by f, isn't it? Because both will be positive. Therefore, we got f1 to be f by 2. So we got f1, we got f2. So the ratio of f1 by f2 will be half, isn't it? So we can write that f1 dot f2 will be f by 2 divided by f. So we are ultimately getting half. So we can see that our answers are matching. That is, we got half here, that is f1 is to f2, and we got half here also. So it just took around 1 minute to solve this. The only concept that you need to remember is focal length depends upon refractive index and radius of curvature. Since here, as you can see, the refractive index and radius of curvature is same, you can use this technique. I hope the concept is clear. This is all about the combination of lengths, and yeah, this is all for this video. If you enjoyed this video, then please give it a thumbs up, and if you haven't subscribed to this channel, then please consider doing so. Till next time, enjoy your studies and build your concept, and I will catch you all in my next video. Bye bye.